because 6, I have 3 more questions in test 8 and I have it all done.
Okay, we'll do section 7 then, okay? Now what I'm going to do, I'm going to do the whole thing. That way it'll be on this recording and I can post it so everybody in the class can see this and it can help them, all right?
Can I still ask questions?
Oh, yeah. Yeah, I want to answer all your questions. But in addition to that, I'm going to work all the problems in chapter 7 so the entire class can see how they're all solved, okay? I got more videos I want to post that explains which some of the meetings I've had, I've gone through kind of the theory or explained what it is that you're doing in these tests, okay? Because if you understand the big picture of what's going on, then when you get to particular problems, you just have to read it carefully and then you already know what to do, right? If you don't really understand how the test works, you're kind of bumping around a little bit in the dark when you're trying to work some of these problems. Like, you know, you did this the last time, but you don't know why you did it, right? And so, but what I'm going to do today, right now, is this part of it. I'm just going to work the problems with and try to keep my explanations to a minimum because I tend to go too long into the explanations and then I don't work very many of the actual problems. So I want to burn through all the problems in assignment 7. And then I will be posting more material in video form, which some of those I've got. I just got to organize it and get it posted so that explain, you know, the general idea of these tests. Okay, so let me load up. Let me go into my stat lab here. I got to load it up. So I'm going to hit this share screen. Now I'm going to close that out for a second. Make sure. Yes, okay, because I've had actually probably 2 or 3 of these meetings where sometimes I'd hit the record button, but then something had happened and we'd stop recording, and then later I would be continuing and forget to hit record again. And so I've lost a lot of information that way. So I'm just making sure for myself that we are recording, and we are. So that's good. Oh, okay. Good deal. So I can hit share screen, and then there's another share button I got to hit here. Now you should be able to see my computer screen, okay?
Yeah.
So, oh, and what I found out, this is a tip for everyone listening. So this is an Apple computer that I'm on. So the browser is Safari. And I found out that a lot of the automatic functions in StatCrunch, when you're trying to load data from a problem, it just doesn't work. And it tells you to turn off, to allow pop-ups, right? To turn off the pop-up blocker in whatever browser you're in. But the browser, I Googled it for Safari, because in Chrome that's easy to do. And I did it in another browser also, but in Safari, and I have like version 12 or 13, it's one of those two, is my version of Safari. And it's actually not supported by that StatLab website. So you can work on the problems, but all the automated stuff where it transfers into StatCrunch, none of that works because the pop-ups are messed up and there's no way to disable them. So it turns out you can. I was a little fearful of that because I've run into trouble when years gone by, but you can download Chrome onto an Apple computer and use that as your browser, and it's not that difficult to do. It's pretty easy, and probably a lot of people already know that, but maybe some people don't. So if you got Safari, you may want to just go ahead and download Chrome. And when you're working on these statistics problems that you know are going to involve StatCrunch, go into the website from Chrome. Don't go into it from Safari. Yeah. And then you can immediately go up and allow pop-ups. You can turn off your blocker. And a lot of times you got to click that 2 or 3 times for some reason. It's a little annoying, but it ends up working. And then all your stat crunch features will work. So I'm going to open up Chrome right now. And we'll go into My Stat Lab. So you see my screen with the Google on it right now? Is that okay? All right. I could hear you there, and then you faded. I couldn't hear the end of what you said. You said something about your microphone. I could hear you talking, and then at the end of it, the volume dropped off, and I couldn't make out what you were saying.
Can I try out on my phone? That's what I'm trying to.
You want to try out what?
Talking.
I heard talking, and that's all I heard. Are you talking about trying to connect on your phone instead of your computer? Is that what you're saying?
No. My phone is either my microphone or Zoom.
Oh yeah. Well, it does. Oh, I see what you're saying. Yes. Let me go back. Just 1 second here. I'm gonna go back into the meeting here and look. Maybe I haven't hit. Yeah, it looks like go ahead and talk on
Can you hear me?
Hello?
Hello?
Yeah, I hear you. I hear you good.
Okay, so can I end the phone call and just talk to you in Zoom?
Yeah, you can.
Okay,
Certainly.
awesome.
Good deal.
All right, awesome, it works.
Okay, all right. So now I'm going to get back. We're going back to share screen, and we're getting into My Stat Lab, which is here. Oh, there's 2 places you have to hit share there. So now you should see My Stat Lab on my computer.
Yeah, I do.
Okay. And you said you're in the afternoon class.
No, in the morning class.
Oh, I'm sorry. My bad. Let me go back. Which they're the same. They're set up almost identically, but I'll go to the morning class here. That thing always pops up dictionary for something. Okay. All right, and then assignments. There's assignments.
Yeah.
Yeah, I clicked on it. I'm still waiting. There. Okay. Then you got to click over here, and it'll allow you to scroll. Okay, and here's assignment 7.
Yeah.
Hypothesis testing means. All right. We're going to do all of these. So I'm going to talk a little bit fast. And we'll go through, and again, I'm going to put other videos up that explain a little bit more of why we do what we do. I made a video last night of this, and I started, I think maybe it was section 8. And I ended up with about an hour and a half of explanation in one problem, and hadn't even worked the whole problem yet. But just for me, it's important to get people to understand what you're actually doing, and not just memorize a few. Oh, you click this to get this number, and you click that to get this number. But you need to know what that means and why you're doing that. Because once you understand that, you have a lot of freedom when you're working the problems. Then you can look at any problem and know what the steps that you need, and you know why you need that step too. And that removes uncertainty and fearfulness. You're not guessing, right? It really reduces your nerves a lot. And it takes a little work to get there sometimes, but it's worth it if you're calm and in control and you own that information. That's your knowledge, you know? So you're better off understanding why you're doing what you're doing.
Yes, very true.
All right, so question 1. All right. And we recognize that for everybody, when you pull these up, everybody gets a different question, but it's a similar type question, okay?
Yeah.
So mine says, hypotheses are always statements about which of the following. Okay, so when we do a hypothesis test, what we're doing is we're testing something to see if a claimed value of a population parameter is true or not. We're testing something and we're either going to reject or not reject some claimed value for a population parameter, okay?
I
So,
just wanted to tell you that it's not showing in the screen. It just shows still the questions.
now that's interesting because I am sharing. Okay, let me see what happens here if I say stop share, and I'm going to try to reshare it and see what happens. Reshare. Oh, okay, maybe. Okay, here was the question. All right, now I'll hit share on that. Do you see the question now?
Yeah, yeah, I see the question.
Oh,
now.
okay, good deal. I think I had this trouble before. So maybe
Yeah.
I got to do that. We'll see what happens on the next question, but maybe we're okay now. All right.
Yeah, hopefully.
Yeah. So population parameter, in a hypothesis test, what you're doing is you go get a sample, right?
Yeah.
And you see what the value of your sample is, and you use that sample to estimate something about the population. In a hypothesis test, you use that sample information to test if the truth of this claimed population parameter, okay, or status quo value of population parameter. So that's always what we're doing. So
Yeah.
check answer, that should be right. Next question. Okay, which of the following is measured by a test statistic? Okay, so this word statistic, that's the key word there, okay?
Mm-hmm.
And anytime you're talking about a statistic, you're talking about something that involves something about the sample. Statistics come from samples, okay?
Yeah.
Quantities of interest in a sample, and let's take, for example, mean, okay? So X bar is a mean, right?
Yeah.
Well, we know X bar is the sample mean. So X bar is a statistic because it's a mean value, but it came from the sample, so it's a statistic. And what was I trying to say there? Anyway, so X bar is the sample mean, and being it came from a sample, that makes it a statistic. Now these words test statistic, okay?
Mm-hmm.
That also means it comes from the sample. So we go collect a sample of something, and if we're in this assignment says up here hypothesis testing for means. So if we're actually testing means, we're testing to see if a population mean is what the claim for it is or not, okay? If the status quo for the population mean is true or not. That's what we're testing. And how we test that is we go get a sample, and from the sample, we get the sample mean, okay? And that is a statistic. X bar is a statistic. And for every value of X bar, there is a test statistic that's associated with that value of X bar. It's either a Z value or a T value, which we'll get into later, but it's one of those two, right? So you have an X bar value, and it has a corresponding either T value or Z value that goes with that particular X bar, okay? So it says choose the correct answer. Level of confidence has in our conclusion. No, I don't think so. How far away from the observed mean? How far away the observed mean lies from the true population mean? Okay, that's actually right. But let's read them all. Probability that the hypothesized mean is correct. That's not
Yep.
true. Okay.
Mm-hmm.
How far away the observed mean lies from the hypothesized value of the population mean. That is more true than B, okay? And here's why. Because we don't, okay, think about what we're testing. Somebody says, hey, here's the value for this population. I'm going to give you a number, 17.
Yeah.
And I'm saying that that is the population mean. According to these researchers or some journal, they've published that the population mean for this whole population on something is 17, okay? And
Mm-hmm.
we're going to do a test to see if we agree with that or not. So we go get a sample. We're going to compare our sample value, what we get on our sample, to that 17 in order to say whether or not we think that 17 is valid, all right? Well, in that situation, if you think about it, we don't know what the true mean is, right? We only know what the claimed mean. This published value that we're testing it to see if our statistics reject that, or they can support that might in fact be the true value. But we don't know what the true value is. That's why we're doing a test. All we have is a claimed value, and another name for that is the null hypothesis, okay? It's the status quo value. And so the test statistic measures how far the observed mean, and this says lies from the true population mean. Well, it doesn't measure that because we don't know where the true population mean is. All we know is what is hypothesized or what is claimed about the true population mean. And that's called the null value of the mean, okay? And that's what we're testing. So the test statistic does measure how far away from the hypothesized value of the population mean our sample is. That's what we measure. When we get a test statistic, we get an X bar. We convert that into either a T or a Z score, one of those two, all right? And then we compare that to the mean value, which has a T or Z score value of 0. I have to draw just one diagram here. And I'm going to try not to do a lot of these again because I want to do a whole separate video that explains the why of everything and try to just work the problems. But I want people to really understand. So this in the side screen here. Okay, so here is our claimed mean, right? Something's published in a magazine that says mu sub naught. That's the claimed population mean. Or researchers have said they think this is the population value. Or we got some other source that's telling us this is the claimed value for the population, okay? So it has some value here in X, all right? And we have a normal distribution. Well, then we also either have a T or a Z score on this same axis, right? And this could be T or Z, and we'll talk about when you use which one. It's not both of them. It's either one or the other. You're just using one of these. But in either case, this value is the 0 value. This would be a T equals 0 if we're using the T scores, or it's a Z equals 0. So what the test statistic is, okay, can you see this picture here very well on your screen, or is it too small?
It's small, but I can see it. It's fine by me right now.
Okay, all right, because I could get out of this and make that bigger. But what we do is we go get our sample, right? It's a random sample. So that means that it could come from anywhere. So if this is the real mean for the true population mean, if this is the value for that true mean, then this shows you the probability of getting a sample at any location in X, okay? So we go grab a sample, and let's say our sample hit right here, okay? This is the X bar that we get from our sample. Okay, so this X bar value gets converted into either a T or a Z. So for right now, we'll just say we're using T, okay? But we could be using either one depending on the problem, and we'll talk about when you use T and when you use Z later. But you take this X bar value, and it has a certain T value that's associated with it, right, on this scale. So what T does is it just measures how many standard deviations away from this mean value, this proposed mean. T just says, how many standard deviations are you away from that? So you get your X bar value, and there's a formula that converts this X bar into its equivalent T value. So that tells you what this T value is. And so this T here, this is a certain value of T, and that's called your test statistic, okay? That's the statistic you got from the test. It's a statistic because it came from the sample. You had to have X bar in order to get this, okay? And so what your test statistic's telling you is just how far away from this mean value you are, right? So the further away from that you are, the less likely that you would get that sample as a random event. If you just got a random sample, there's a low chance it would fall here, right? Because this curve tells you what the probability, relative probability of getting any point on this axis is. It's right here, right? And if we get an X bar bigger than that, it's an even smaller probability that we're going to get it. So this test statistic measures this distance is what it does. How far is your X bar from the proposed mean? But it does it in a particular way. It says T equals X bar minus mu sub naught. Okay, that is the distance, right? X bar minus mu naught is this distance. But then you divide it by standard error. And what standard error is how wide these standard deviations are, right? So that's what this test statistic is. It's counting how many standard errors, which is a special form of standard deviation, right? The standard error is the standard deviation for the X bars, okay? So this is +1, +2, -1, -2, just like on Z-scores. Only now we're talking about a T-scale, but it's the same thing. This -1 means you're one standard deviation or one standard error below the mean. Your two standard errors below the mean. Okay, and how big is a standard error? A standard error is how is the width of one of these. That's what the standard error is. And these are all the same width because we're going in increments of 1, all right? And the standard error has a formula. S over square root of n. That's how you get it. So anyway, the idea here is your test statistic is really counting how many standard errors, or you can think of it as standard deviations. It's the standard deviation of the X bars, right? That's what standard error is for means. It's the standard deviation of the X bars. How many of those are we away from the mean? So here's the difference. If we divide it by the width of one standard error, that tells us how many standard errors. So this is like a count of how many standard errors away from the mean you are. So the higher this value, the more likely you're going to reject this as being true. You know, if we get an X way out here, we're more likely to reject this than if we got an X that was in here somewhere, we're not going to reject this, right? Because we're going to say if that's the true mean, there's a high probability a random sample would occur here. But there's a very, very low probability a random sample would occur out here somewhere if this is the true mean, where the true mean is, okay? Yeah. That's what you're doing with a test statistic. And really what you do is you compare your test statistic with the critical value of t, which is called t star, okay? And t star is a number that we determine. We determine what this t star is. And t star depends on the confidence level you're testing at, and also the degrees of freedom, and this is minus t star. It's easier to talk about if you're doing z's, okay, but it's the same exact idea. If these are z's, then the only thing that determines what this value is, what the critical value of it is the confidence level, okay? But if it's a t, you need the confidence level and a thing called the degrees of freedom to determine what this number is. But your test that you're conducting is you're going to compare your test statistic with this value, with the critical value, and see where does this test statistic hit in relation to that. And this is at a specified confidence level, okay? Usually it's 95%. Usually, but there are others. But anyway, let me get back. See, I'm going into explanations again and not working the problem. So let's do the problem. Which of the following is measured by the test statistic? It's how far the observed mean. So that's your X bar. That's your observed mean, right?
Yeah.
Your sample is from the hypothesized or from the claimed value, which is the null hypothesis value of the population mean. So in a statistical test, the first thing you do is state the null hypothesis, and you say mu sub naught, and that naught just means that this is the null value. This is the mean that you're saying is the null value, and then you state what it is or what the claim is, okay? So how far the observed mean, the sample mean, lies from the hypothesized value of the population mean, that would be this mu sub naught. That's the null mean. Okay, I'll beat that to death, but that's that problem. So let's go to the next question. Okay, a random sample, 10 independently healthy people. It's got these body temperatures, and this says test the hypothesis that that says population mean there is not 98.6 using a significance level of 0.05. Okay, so the null hypothesis is then, okay, so what we're testing is we're testing this hypothesis that the population mean is not 98.6. That's what we're testing, right?
Yeah.
So you would say, what you would say there is your null hypothesis is that the population mean, the null value, mu sub naught, okay, is 98.4. That's the null, right? And null means no difference. That's what null means. So we're saying the status quo, there's no real change from that. The status quo is 98.4. They want us to test if this mu naught is not, how do they say it? They just say is not 98.6. So that gives us this alternative hypothesis, okay, which is H sub A for alternative. And that hypothesis, it says is not 98.6. So is not becomes not equal to. And I wrote 98.4 here for some reason. This was supposed to be 98.6. So the alternative is mu sub naught is not equal to 98.6. So that's the statement of the test that you're doing, okay?
Yeah.
The key thing here to note in this is the fact that we have a not equal sign. because there's three different kinds of tests that we could do.
Yeah.
This could have said the alternative, instead of saying not equal to, the alternative could be that mu sub naught is greater than 98.6. And that's a test, right? There's another test. They all have the same null value, but the alternative, there's another one where the alternative says that this is less than 98.6. So there's three different tests we could do. We could test to see if it's less than this, test to see if this is greater than this, or we can just test to see if it's not equal to this. And this problem is telling us to do the not equal. Okay, so anytime you have a not equal in your alternative hypothesis, it means you're doing it's called a two-tailed test, okay? So you're going to have your critical value for your statistic, whether it's a t or a z, okay? And let me think here just 1 minute. Okay, this would end up being a t-test here. So this is the critical value here. You're going to have, this thing is always symmetric, so you're going to have another one exactly the same distance on the other side, okay? And this will have the value minus t star. So whatever number this is, it's the same number over here. It just gets a negative sign in front of it, okay? And this test we're going to do, we're going to go get a sample, which will give us an x bar. We're going to convert that x bar into a t-value. And that t-value is called the test statistic. And then we just see where that t-value lands. If it lands out here outside this critical value, we're going to reject that the true null really lives here where we said it did. Or if it lies outside this one, we're going to reject it. That the true null lives where we said it lived, or where the claim said it lived, okay? But if our test statistic ends up being inside of these values anywhere, then we cannot reject it. Now, when we cannot reject it, it doesn't mean that it is definitely what it said it was. It just means it might be, that we can't rule that out. It could be that value, but it could be some other value that's close to that, but not that. But when we reject it, we're saying absolutely that it is not that value, okay? And to reject it, we have to be outside of these critical t's. So these are called rejection regions, okay? Rejection region. And you got one over here too, same thing, all right? So that's what we're doing in the test. So let's get back to the problem. It says, which of the following correctly states the null hypothesis H sub O and the alternative hypothesis H sub A? So the null is always going to be mu equals some value, and the value that they want us to use here is 98.6. Okay, that's what we're testing. So HO is going to be mu equals 98.6. HA, the alternative, is we're testing that it is not 98.6. So HA has to say not equal to. So we come down here, this is right for the null. It's also correct for HA because it says mu is not equal to 98.6. Well, that is a two-tailed test. So that one's correct. We don't even need to read these because we know this is the right answer, okay? So we move on. All right, it liked that. Maybe we'll get lucky here and get 100 on this. Who knows? All right, so next part says, step 2, a stem plot is shown that is not strongly skewed, suggesting the distribution of the population is also approximately normal. A histogram would be appropriate, okay? So this is a stem plot here it's showing you. You see that?
Yeah, I do.
So what a stem plot is, you can think of it as kind of a sideways histogram, right?
Yeah.
If we would rotate this thing 90 degrees and stand it up on top of these 96, these would be at the base of it, then this shape here would be like the histogram, right? And they're just showing you, this is just like a quick summary of the data. that we had 8 at temperature 96. We had 29 of them that were at temperature 97. We had 12. Well, no, actually, okay, I misstated that a little bit. Let me back up here. I got ahead of myself. In a Stemplot, which is what this is, it does have the shape of a sideways histogram. That's correct, okay? But what this is, this 8 here means we had a single value at 96.8. This 29 means we had a value at 97.2, and we had another occurrence that was 97.9. Here we had an occurrence that was 98.1. We had another one 98.2. We had a 98.4. We had a 98.5. So they're showing you this because this is something you can do on pencil and paper real quick. You don't need a computer.
Yeah.
You can just write these down this way, and it gives you the general shape of a histogram. It's sideways, so you gotta, kind of tilt your head a little bit to see, the normal histogram shape of it. Okay, but each digit in here is an occurrence of this value, and this is saying where more precision of that value. So we had a 96, but we had a 96.8. Here we had a 97, it was a 97.2. We had another 97, but it was a 97.9, right? That's what a Stemplot does. So that's handy because just pencil and paper, no technology, you can do that real fast. So all they're saying in this problem is that they did this, and that this is approximately has a normal shape. It's not great, but it's not bad. It's not like, it doesn't have a strong pattern of drop off as you increase or rise as you increase. It's kind of sort of symmetric and has a general appearance. So they're just using that to say, okay, it's fair to say that the population based on this sample we have is probably approximately normal. That being the case, that allows us to use these central limit theorem statistics that we use to do these tests that we do. Because the population is normal, okay? And here were the temperatures up here. These are the same temperatures. So which I think, yeah, see here's 96.8, here's 96.8. So there's a 97.2 in this list. We go across here, here it is, right? So this is the diagram of this data here. So the next important question here is, I got to move this window out of the way. How big is our sample? How many items are in our sample? How many individual X's make up our single X bar that we have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We got 10. So N, the sample size, equals 10. We need to know that. Okay. Since we have a normal population and we have a small sample size, and small just means when you're talking about means testing, if N is less than 25, that's a small sample. If N is greater than or equal to 25, that's considered a large sample, okay? If you have a small sample and a normal population, you do a t-test. So we know right away now we're going to be using a t-statistic, not z, okay? And it's just because of the sample size is low, it's small, and we have a normal, and I've put this up on Blackboard before, but I'll do it real quick just to show you. Here's a normal population and not normal population, okay? And then here we have a small sample size, small sample size. And
Here
here
you could put it full screen on this one so we can see it.
Yeah, let me I think I have to hit stop share. Okay.
Yeah, there we go.
And then if I double click this, there, how's that?
Yeah, that's perfect.
Okay, so large sample size. So this is n less than 25. This is n greater than or equal to 25, okay? When we have a normal population and a small sample size, n is less than 25, we use the t statistic. When we have a normal population and a large sample size, we use z, okay? If we have a not normal population, but we have a large sample size, n greater than 25, but our population is not normal, we can use a t. We're allowed to use a t, okay? That just leaves this case here. Not a normal population, and we have a small sample size. Well, this case is no good for anything. We can't do any of these central limit theorem statistics. If we have a small sample size, and if we have reason to suspect that our population does not have a normal distribution, it wasn't done from a large population of random independent samples, because that would give you a normal distribution generally. But anyway, for whatever reason, if you do not have a normal distribution for your population and you have a small sample size, you're done. You can't do statistics there. So you just have three cases to concern yourself with. And you can see here that most of the time you're using t and not z, okay? Very brief explanation here just to show you about t and z. Okay, there is only one z distribution, okay? So z is kind of nice. It's simpler. It's you need less information to use z than you do t, right? Because your z star value, your critical z, okay, which over here, if we're doing a two-tailed test, this would be minus z star. And so remember, on z-scores, this is 0, and we're counting standard errors here, right? 1, 2, 3, -1, -2, and all these values, you know, on this line are possible. But anyway, for a z distribution, z star is determined from only the confidence level. That's all you need, and you get what z star is, okay? And so you give me a confidence level, and I'll tell you what this value here is, which is z star. You give me a different confidence level, it's going to be a different value. And you look that up in a table, or you use technology to get it. So speaking of technology, I'm going to do that real fast because this is worth seeing a couple times. It's very helpful to understand this. Let me go back to share screen.
All right.
And we're going to go into StatCrunch, or we'll go back into the, now I need to share that. Well, no, let me go ahead and let me see if it'll let me open before I share. See what happens here. See if I still have it. No, I can't share it from there. So I gotta close. Yeah, we don't want that. Okay, stop share. There we go. Okay, let me get back here now. Stop share. Let's go share screen again. There, okay. Now I'm gonna go ahead and, well, I'm gonna click on, where's the, oh, okay, well, I've already busted out of that problem here, evidently. It's closed out of that particular problem. I'll go back into the assignment here. Question 1. Okay, we're back where we needed to be. All right, so, but I can't, you don't see that, right?
Yeah, I don't see anything right now.
So I gotta go back. I can't, let's say stop share. Okay, let's share screen. Here's what we do. We do one click and we don't double click. Okay, now I can hit share. Now you can see it, right?
Yeah, I can see it now.
Okay, so I'm going to go into StatCrunch now, all right? So I can do that here. I can question help, and since I'm in Chrome, it'll work. I'll say StatCrunch. And this happens sometimes, says, oops, there's a problem. But what I found is that you just keep doing it and it ends up working, okay? A lot of times it works on the second time. I have no idea why, but like it's going to work now. Okay. I just want to show you.
By the way, we can't see the StatCrunch page.
You can?
I can't.
You cannot see it.
Yeah.
Oh, okay. I had this working earlier too. So let me see if I minimize that. No, I need to go. Oh, wait a minute. I want to, well, I minimized it. So how do I unminimize it now? Doggone it. See, I don't see where it put it. Let's say stop share again. All right, let's go back into share screen. Here's the problem. One click, we say share. Okay, now, okay, oops, I'm going to say new share. When can I do that? Let's see if let me open it and see if it'll let me do this new share after I open it. So, StatCrunch. Okay, I'm going to say new share here, new share. Now it should have StatCrunch there. And share.
Yeah, there we go.
All right, good deal. It's tricky. All right,
Yeah.
so what I want to show you is where you get Z star from, okay?
All right.
So remember, there's only one Z distribution, right?
Mm-hmm.
So Z star, it just depends on what your confidence level is. You put a different confidence level, you get a different Z star. But it's always the same one. If you give it the same confidence level, it's always the same number. So once you know what those numbers are, you don't even have to compute that, right? So that's nice. So I'm clicking on Stat here, Calculators, and I'm going to say normal. So the normal calculator. Okay, now we've been talking about two-tailed tests, right? Because of that, I'm going to use this between function here, all right? Because we're talking about two-tailed tests right now for these Z star. So we have a Z star and we have a minus Z star. It's the same value, just has a negative sign, right? And we want to know how we determine what Z star is. So we come down here and notice we have mean 0 and standard deviation 1. So if you don't have that here, you put that there. That leads this thing into a Z calculator. Even though it says X, it's really Z. This is Z equals 0, Z equal 1, Z equal 2. So remember, these are those standard errors, right? This is 1 standard error, 2 standard errors, 3 standard errors. Okay, and then here, our confidence level, if it wants to, okay, and our problem said to test it at a 0.05 significance level, okay? Well, the significance level is related to the confidence level. It's just a simple subtraction. 1 minus the significance level is the confidence level, okay? So 1 minus 0.05, because it said test at a 0.05 significance level. So 1 minus 0.05 is 0.95. So that's a 95% confidence level. So we put our confidence level out here, but we write it as a probability. So it's 0.95. Then we say compute, and there's our Z star. So this Z star here, notice we're not quite at 2 standard errors or 2 standard deviations. We're just a little bit below that, right? 1.96.
Yeah.
Okay, and then the negative Z star is negative 1.96. So this never changes. If you know you're testing at a 0.05 significance level, which is the same thing as saying, hey, I'm testing at a 95% confidence level, then you know your Z star is 1.96 and you're done. You don't have to calculate it. And this is the one that's used most often, right? So that's good to know. And also remember, this is not really X here because this is a Z score, because we've got a mean of 0 and a standard deviation of 1. That makes this normal curve into the Z distribution. That is called the standard normal curve, okay, which is Z scores. So this is the probability that Z is between these two numbers is 0.95, okay? So that's our critical Z. So I'm going to write that down. So at 95% confidence, Z star equals 1.96. And remember, this is for a 2-tailed test also. If you're doing a 1-tailed test, it's a different number, because the 2-tail means that 5% of our probability is contained from both of these, right? So really you have 2.5% in each one, okay? So the probability that you're above this value really is just 2.5%, but the probability that you're below this is 2.5%. Anyway, we've got this value now for a 95% confidence level.
Mm-hmm.
Let's do a 90% confidence level and see what that is. So Z star equals 1.6449, and that's a 90% confidence level, okay? And notice what happened there in the picture. Notice this red region is narrower than it was, right? We're not out close to 2 anymore. We're in a little bit. So this is what I was talking about earlier in the semester, that as your confidence level gets smaller, we went from 95 to 90% confidence, okay? But we're able to specify a narrower range to somebody. So if we were giving somebody the confidence interval on something, it would be a narrower range at 90% confidence than it would be at 95% confidence, right? And the reason is remember what this is where you get a random sample. What's the probability that it occurs between these two critical values? And the lower your confidence, the narrower that's going to be, because there's more probability, there's more chance for error, so there's more probability that you're outside of that, right? So anyway, I'll write down the value here. Z star is 1.6449 for 90% confidence. Let's do another one. Let's say 99% confident and see what it is. So what will happen here? We will have a much wider range, right? So we look at that and we do. Look, we're way out past 2 here. So we're 99% confident if you get a random sample from here, if the true mean is really located here for the population, if the true mean for the population is in fact located where this says it is, at this 0 point, then we're 99% sure that any random sample you take would occur between here and here, okay? So to reject this value at a 99% confidence level, we have to be way out here in one of these tails before we can reject it at 99% confidence, okay? Do you see that? Does that make sense?
Yeah.
Okay. So I'll write that down. Z star.
Is this part of the question, or are you just
Well,
explaining right now?
yeah, it is the explanation, but it's like I can't help myself. I want.
Yeah, it's fine. I was just making sure.
Yeah. So Z star here is 2.5758, and that is for a 99% confidence level. Well, I really messed that up there. It's percent. Okay. So can you see this here? Okay.
I can see the stack crunch in the. No, yeah, I can see it.
Okay. So you see at the higher confidence, our Z star is a bigger number, right? The
Yeah.
wins are way out wider as our confidence goes up. But that means, remember what we're doing is we're estimating something for somebody, right? So we can give them a narrower error bracket, if you will, around our estimate. We can give them a narrower region on the estimate, but when we do, our confidence is less. We have to do that at a lower confidence level. We could say, oh, and you could do that for any confidence level. We could say, if we want this to be from -1 to +1, let's just put it in here and see what we get, just out of curiosity, okay? So -1 to +1, compute. So this is a 68.3% confidence level, okay? We're 68% certain that if the true mean is really here and we do a random sample, that it'll fall in this area. Okay, that's enough of that. Let me get back to the actual problem.
All right.
I click here. We've lost it again. There. Okay, do you see that?
Yeah, I can see that.
Okay, good. So it says comment on the data collection and state the test to be used. Well, we said because of our sample size and the fact we have a normal population and a small sample, n is 10, which is way less than 25. We know it's a t-test.
Yeah, so it's
So the sample always has to be random, okay?
Yeah,
It needs to be valid. And the observations always have to be independent. So if I go get an X and then I go get another X, that second one can't have anything to do with the first one. It has to be totally independent from that, unrelated, right?
Yeah.
No connection between those two, okay? It says use the, okay, and how many samples do we have here? We actually just have one sample. It's got 10 values, n equals 10, but it's one sample, and we've said we're doing a t-test because we have a small sample size. Okay, and the significance level is, and it told us that up here, it wanted to do this test at a significance level of 0.05, which is the same thing as a 0.95 confidence level, okay, so 0.05. So check answer, it liked that.
Yeah.
All right, it says find the test statistic, okay, so now we're going to use StatCrunch. I'm trying to think of how to make sure StatCrunch comes up again. Let me see. Because if I just go here, I think it maybe doesn't come up. So I'm going to stop share. And then well, share screen. Okay, I go back into the problem. I share the problem. If I go here in StatCrunch, I think. Okay, now maybe you don't see that now, right? You do not.
No, I just see the question.
Okay, you don't see StatCrunch. So let me go over here and hit stop share, and then share screen. Yeah, now I can select StatCrunch because it's an option, and then I can share. Good. Okay, we pulled it off, right?
Yeah.
Except I should have dumped that data in here, which I didn't do. So let me go back. I'll close StatCrunch. Okay. Okay. All right. Share screen. Go here. Share that. Okay, so maybe there's an icon here. We can do this test with the eye. It wants the test statistic, okay?
Mm-hmm.
There's a couple different ways you can get that. So we'll go here. I'm going to put it in StatCrunch. Oh, well, it gives us a nice report already. Do you see the report?
Yeah, I see the report.
Okay, good. Well, we've got all the information we need because somebody used StatCrunch and it generated this report. Okay, and I'll show you how to do that too later. But
all right,
here's the important things. Okay, it gave us our X bar for that sample. It's 98.24. That's the sample mean. Here's the standard error of the mean. Okay, so that is the standard error. That's how big the standard deviations are of X bars. If we would repeatedly go get many, many X bars and estimate what their standard deviation is, it would be this number. That's called the standard error, and that's the standard deviation of it's called the sampling distribution, which basically means it's the distribution of the X bars, okay? But and here it gave us a 95% confidence interval already, all right? And it calculated, and notice it used a t-test. It didn't use z. But this value here, this is called the test statistic. This came from your sample. This has nothing to do with the critical t or t star. That comes from a lookup table or technology to calculate what it is. But this is the test statistic. It comes from the sample and it's already been calculated. It's minus 1.43. So what that means is we're 1.43 standard deviations or standard errors. We're 1.43 of these below what the proposed mean is, okay?
Yeah.
And typically to reject a null value for a mean, you're going to be somewhere around 3 standard deviations away or even more, okay? If you're 1 point something away from it, you're not going to reject it because you could get that by chance very easily if that's the real value. But it wants to know what t is. We can just put it in here, minus 1.43. Okay, enter. Okay, it liked that. And p-value, well, it gave us the p-value already, okay? 0.188, 0.188. And it liked that. Now, let me go show you how we could have got these ourselves, okay? Couple different ways, because all these problems are a little different, right?
Yeah.
This one was nice because it just gave you this already, but sometimes they won't, and you got to go get it, okay?
Mm-hmm.
So let's open. Oh, here we go.
It's that right side one, yeah.
Yeah, that'll put it in StatCrunch. Okay, and now I'm going to go stat.
You have to do the stop sharing and share because it doesn't show.
Yeah. I have to wait till I get to the final screen and then share it.
Oh, okay.
Yeah, so this screen is it's like the first StatCrunch screen, okay? And the only thing it has the data in the left-hand column, the screen I'm looking at right now, okay? So it just put the individual X's in the left-hand column. That's the only thing in StatCrunch. Or maybe I could share, I could share this screen, I guess. Let me say stop share, share screen, select share. Okay, now you see it?
Yeah, I see it now.
Okay, so you go stat, and we can do t-stats here, okay?
All right.
Stat and t-stats. It's one sample,
Yeah.
right? There's 10 individual x's, but that would be one x bar for that whole column. So that's one sample. And we actually have the data, right? We have the individual x's. So we'll select with data.
All right.
Okay. Now, maybe you don't see this one, right?
Yeah, I see it.
Oh, you do see it. Good.
Yeah.
Okay, so we got to tell it, yeah, that is the data. It's in column 1.
Mm-hmm.
And now we're doing this t-test here.
Yeah.
I was trying to think. It wants a well, we can just click compute. Yeah, okay. I'm going to select confidence interval, okay?
All right.
And we're not testing null hypothesis yet. We don't need to.
Yeah.
We're doing the t-test. Well, actually, let's do this. Yeah, let's do the null hypothesis.
All
So
right.
we have to put in the value here. What was the null value, the proposed value for the population mean? I think they said it was 98.6, right?
Yes.
So we put that in there for HO, H sub naught, okay? We're saying the hypothesized population mean, mu, is equal to 98.6. Okay, and our HA, it said we wanted to test that it was not 98.6. So we've already got that here. We got not equal to, right? You could click on these and either choose less than, greater, or not equal to. Well, the problem told us is not that, so we choose not equal to. So we know we're doing a two-tailed test.
Yeah.
And we say compute. And there's the values we were looking at before, okay? That report it gave us earlier, these are the values.
Yeah, I
So
see it.
we got the sample mean here, which that's nice. Here's our t-value. So this is our test statistic. It's a t-value. It's a t-score, if you will. You've heard that term z-score. Well,
Yeah.
this is the t-score. So that's a test statistic. Here's the p-value. So we've got all that stuff right there. There's another way you can get this, right? Let me go over here. To get this t-value, there's another way to get it, okay? Just what the test statistic value is. Because you might not have all this information presented this way, right? It may give it to you a different way. So the test statistic, and when we're testing means, it doesn't matter whether we're talking about Z or T. It's the same formula for either one. So that's kind of nice, right?
Yeah.
But here we're using T. So our test statistic is T. And that's calculated. You just take the sample mean minus the proposed population mean, the null value for the population mean, and divide it by the standard error. Well, we mentioned this earlier today already, but so that's what the value of the test statistic T is. So if we plug X bar in here, that 98.24, and we plug in this 98.6 was the value we were testing, and then we plug in our standard error, which this other report gave us, 0.2526, and we just do this subtraction and divide by this. We get the same value that they gave us in that report we saw, okay? And if you were calculating this by hand, so you get this from the sample, right? And this is given to you in the problem, or you stated in the beginning of the problem what the null value is for the mean. So the only thing maybe that we're not sure about, well, what is this thing? And that for means, standard error is just S over square root of n, okay? So S is the sample standard deviation, and n is the sample size, which for us was 10, right? So if we get the sample, and I'll do that here. You can still see this screen.
Yeah.
So I'm going to say summary stats for our data. Okay, so we just go stat, summary stats. We tell it it's column 1. So we select it and we just say compute. Okay.
Yeah.
Well, it gave us the standard error, so we don't even have to calculate it. There it is. But we could calculate it. Okay.
Yeah.
We take the standard deviation, which is here, so this is S. This is the sample standard deviation. And we just divide that by the square root of n, and it gives us n here. Our sample size was 10.
Yeah.
So this number divided by the square root of 10 will give us this number if we didn't already have it. That's the standard error. That's how much so if the samples, and this is a good place to see this, so the individual samples have kind of this much variation, right? But if we get an average of 10 and go get another average of 10 and another average of 10, the deviation of those averages is only this much, okay? That's a good place to see what that means right there. So this individual x's, standard deviation of them in a single sample. This is if we had a whole bunch of samples and looked at the standard deviation of the x bars. And the thing is, if we increase n here, if say this goes to 100 instead of 10, then this number will be a lot smaller, right? It's just telling you that the more samples you have in your average, you're reducing the variation of those sample averages. If you repeatedly sample, those averages will be closer together than they will be if n was 10. If we had n equals 100 and in a whole bunch of x bars, we would have a much smaller standard error than we've got here because we only had 10 in our sample. So that's a nice place to see that. The individuals vary this much. The averages of 10 only vary this much. But if we'd averaged 100, this number would be even less, okay? So anyway, that's how we get standard error. And so that's how we would get, we could calculate back to this thing over here, we calculate T. See if I can blow that up. Say stop share. Well, and you see it there. So to calculate T, x bar minus mu sub naught divided by standard error. That is our test statistic, okay?
But is that NO?
It's mu sub O. It looks like a U. It's a lowercase, it's called the lowercase mu character. So it's a Greek letter, and it's pronounced M-E-W, mu, but it kind of looks like a U usually. For whatever reason, they don't draw the other part of the M on the other side. So it looks like a U kind of, but it's mu. It's a lowercase m, but the Greek letter, and they call that mu. And the 0 just means that's the value for the null. That's the one that we're proposing is the true population mean. We don't know if it is or not, but that's what the claim is, right? That's the status quo value. We put that little 0. So that tells us which mean we're talking about there. And then x bar is the sample mean. So this is the distance of your sample mean, how far it is from the proposed population mean, and then we're counting how many standard errors make up that distance, right? When you divide by this, that's like a count of how many of these things in the bottom it takes to make this distance here, this difference. So that's the test statistic. Let me go back to the problem. I think I got to go back to share again. Where's the problem? This was the problem. And share. Okay, and I'm in StatCrunch. And so let's see what the next part of the problem wants here. See, the only thing I'm not sure about, when you click, if I click minimize, Oh, I see. It's down here. Okay. So here's the problem. And let's move that. We had this nice report that gave us the information we wanted.
Yeah.
This says interpret, reject or do not reject the null hypothesis, HO, and choose correct interpretation below. I don't know if we can see all of this. This thing here is kind of there. That's better. Okay. So here's our p-value. I didn't show you exactly what p-value is there yet. Let me see if I can pull this up. Talk about p-value for just a minute. Stat. Have you got plenty of time, Ruben?
Yeah, I got all day.
Okay.
So I'm no rush.
We'll just keep going then.
Yeah, I'm fine.
Okay, so stat. I'm going to use a calculator and a t-calculator to show you what p-value is, okay?
All right.
And we were doing a two-tailed test because our alternative hypothesis said not equal, so we'll say between. That'll convert this into a two-tailed test, okay? Then we have to enter our degrees of freedom, which is n minus 1, and n was 10, right? So the degrees of freedom is going to be 9. Now, why do we do that? Okay, this is the difference between T and Z. With Z, you don't need any of this. All you need for the Z scores, if you want to determine a Z star or a critical value of Z, all you need to know is what confidence level are you talking about. You put that in, you get the value of Z star that goes with that confidence level, and it's always the same number. It doesn't change, okay? That's because there's only one Z distribution. And what determines where you are on that is only your confidence level, or it's a probability. That's the only thing that determines where the point is on that curve. So Z-scores are very simple. You just need confidence level. T-scores, you need confidence level. That tells you where on the curve you are, but each curve has its there is a different curve for each degree of freedom. So if I've got 9 degrees of freedom, that specifies a certain curve, right? If I've got 150 degrees of freedom, that's a different curve. They all look kind of like a normal distribution, but they're slightly different, right? There's a little more slack, if you will, in the T distribution because there's more uncertainty in it, because our sample sizes are small for T distributions. So you don't have as much certainty in that curve, and because of that, they build in a little slack in it. They give you different curves depending on how big your sample size is in order to compensate for that uncertainty. So when you put a degree of freedom of 9 in, that's really telling it which curve it's going to use, okay? There's a T distribution that is associated with 9 degrees of freedom. It goes and grabs that curve. If you put 25 for degrees of freedom, that specifies a different curve. And again, they all look kind of alike. So you never notice that when you see a graph, you just see a curve. But it's a very particular one. It's either in the computer, it calculates it, or you look it up in a table, right? When you go get a critical value for T in a table, you have to tell it, you have to look up what's the degrees of freedom, and that tells you which row to look across. Well, that's because each row is actually a different T curve. And then you go across the rows and you find the confidence level that you're interested in, and that intersection gives you the value of T for that confidence level at that degree of freedom. So that's everything you need to know about T distributions, okay? So the Z's are simpler. It's just confidence level. A T distribution is confidence level and degrees of freedom. So for our sample, we had 9 degrees of freedom. And then if we want to test at a point at a 95% confidence level, we put that in, and it
By the
gives.
way, it's not showing the
Oh, okay, okay. So let me go back and share again. Share screen, select, there, okay?
Oh, yeah, there we go.
So I put 9 degrees of freedom, and that tells it which curve to use, because if I put a different number in here, it actually draws a different curve, okay? That's not the same curve we were just looking at. There's a different curve for every degree of freedom value, okay? And then I don't know why it did this. I'll set this back to just 9.5 exactly. Okay, so here's what p-value is, okay? You see the tails on this thing here? The white areas out at the ends? The p-value is for a two-tailed test, it's the total probability that you're outside of this red area. That's what your p-value is. So this thing gives you the probability that you're inside the red area, and that's 0.95. So for a 95% confidence interval, there's a 95% chance you're inside this red area, which means you're inside those critical t values there. T star is 2.2622 and negative t star is minus 2.2622, okay? So this number out here, 0.95, that's a probability that you're inside the red region, that you have not exceeded your critical values. What's the probability that you do exceed it? If you get a random sample, what's the probability that it will not be inside that range of critical t values? Well, the probability is 1 minus 0.95, so there's a 5% chance that you'll be outside that red area. 2.5% chance you're in the right tail and 2.5% chance you're in the left tail. But altogether, it's a 5% chance that you're not in there. And that 5%, that 0.05, that is the p-value, okay? So that's the probability. The p-value, let me write this down. The p-value is the probability that you obtain a test statistic, which would be a t value. So we go get a random sample, we see what t is for that. That is at least extreme as t star or minus t star. And what do we mean by extreme? Extreme means that it's at least as far away from the center, at least as far away from the mean as t star is, or minus t star, okay? So that's what the p-value is. It's the probability, which is the area that's in those tails outside the limit. So now I get back to the problem. It says interpret, reject or do not reject HO. Okay, so our p-value was 0.188, it turned out, for this problem.
Yeah, you have to unshare.
Oh, okay, okay. Thank you. Stop share, share, select it, reshare. Got it. Okay, so the p-value that it already calculated, we got from that report, right? That report had it in it already, but we could have calculated that ourselves. We could get a 95% confidence. Well, you don't know. I'm sorry, not the confidence interval, but we just take the t value and we put it in that calculator, the test statistic value, we enter that as our t value in that calculator. And that gives us, and we do the between function, that gives us the probability that we're between t equal minus 1.43 and t equal plus 1.43. that gives us the probability that we're between those values. The p-value is the probability that we're outside of those values. So we just subtract that probability from 1. So 1 minus the probability that we're between minus 1.43t up to positive 1.43 for t. The probability that we're in between there, we subtract that from 1, and that gives us our p-value, okay, which this report already did. It says it's 0.188. So it says interpret down here, reject or do not reject the null. So remember, we're testing at a certain confidence level. What confidence level are we testing at? It said using a significance level of 0.05. So that means we're testing at a 95% confidence level. So at 95% confidence, here's how this works. You look at your p-value. If the p-value is less than your significance level, that means it's further out in the tail than the t-star is, okay? That it's way out in the wings. If this p-value is very small, if it's smaller than this number, it's more extreme than this number. And that's when we reject the null. So if the p-value is not less than your significance level, then you do not reject the null, okay? So here p is 0.188. That's actually bigger than 0.05. So we're not going to reject it, okay? And we could also see that you can get an idea of that by looking at the t-value, right? This says we're 1.43 standard deviations away from the proposed mean. Well, that's not a huge distance. If you remember from like our empirical rule, it was like 68% or about 2/3 of the data were actually within plus or minus 1 standard deviation. Well, this is a little more than that, but it's not even out to 2 standard deviations yet. So it's going to be a fairly high probability that you're within from minus 1.43 to plus 1.43. Let me go back to, let me see if I could go back to StatCrunch again and show you that again. Let's see. And I'll have to stop share and reshare. Let's see. Well, let's get into it first here. Oh, maybe that was down here. No. Okay, it's closed now. So StatCrunch. Okay, stop share, reshare, select StatCrunch, share. Okay, let's go here to stat and let's go to T calculator. So calculator, T, all right, T calculator. And our degree of freedom was 9. Let's put that in there. And let's do the between thing. And now go over here and see. Oh, it doesn't have the. I did that. I lost StatCrunch there. That's not it. Let's go back into the question. Okay. Well, I'm going to leave that StatCrunch alone for now. It's getting too complicated. We're just going to work the problem, which is what I was supposed to be doing here, and not all the explanations again. You see the problem screen in front of you still, Ruben?
No, I see the StatCrunch right now.
Oh, you see StatCrunch?
Yeah.
See, I don't see StatCrunch.
Oh.
Well,
Yeah.
I can't see where StatCrunch is. I see another window on here.
You have to probably stop sharing and share again.
Yeah. Oh, I see StatCrunch. Yeah, I see it. Okay, good. I don't remember the exact number. It was 1.4 something for that t that it gave us. Do you remember what it was? It's not super important. I'm just showing you the general idea. So I'll say minus 1 point. Let's say it was minus 1.42, for example. Okay.
yeah, mine was different than yours.
Oh, okay. To plus 1.42. And we say compute. Okay, so the probability that a random sample will be inside of those critical t stars, okay, from negative t star to plus t star is pretty high, okay? So if we just get a random sample from here, there's a pretty good chance that it'll hit somewhere from here to here, because this is high probabilities, and these are very high probabilities, right? So what you were saying is if we get a sample in here, we're not going to reject that this is the true null, because there's a good chance that is the true null. If our random sample hits in here, we're pretty close to it. We're only 1.42 standard errors away from this center, right? And so our p-value here, in this case, okay, if we got a random sample out of this thing, our p-value would be the probability that we get something outside of this. So we would take 1 minus 0.81. Our p-value would be about 0.19, which is pretty high. So there's a somewhat high probability that we could get in these tails by chance. 19% of the time, even if this is the real value, we're just by chance we're going to hit out here. So that being the case, we're not going to reject it because we're testing it at the 0.05 level, right? And 0.05 in the tails would be way out here somewhere. It had to be way out past that for there only be 0.05 area in these two tails combined, okay? So that's what I was going to show you about p-value. This has a pretty high p-value, the probability of being outside the tail, relatively high. And we're testing it at the 0.05 significance level, where you can think of that significance level as kind of a threshold p-value level. We're testing it at a 0.05 as our threshold for what's going to pass or fail for p. If we're less than 0.05, we're going to reject, okay, because it means we're way out here in a tail. But if we're greater than 0.05, we're not going to reject. And at these t values, which we got for our actual sample, the probability of being right next to it and just out a little bit is actually fairly high just by chance. So we're not going to reject this. That's what I wanted to show you. Let me get back to the problem here. I can't see it. I'll do stop share and maybe I can find it again that way. There. Share. Well, for some reason, okay, it's showing StatCrunch, which I'll just minimize it maybe. There. Okay, you can see that, right?
Yeah, I can see the screen right now.
Okay, it says interpret. So we're not going to reject because our p-value, just like I was showing you there, is pretty high. Especially what you're comparing it to is this value. This is the level you're testing against. So this significance level, this is a p-value. This is the critical value. If we were testing at 95% confidence, this would be the p-value we would have. So we have to be less than that before we're going to fail and reject it, okay? And we're pretty big. So we do not reject. We cannot reject it as a population mean from these data at the point. So that's true. It says we cannot reject. And this one says the population mean is definitely 98.6 on the basis of these data. That is not true. All we can say is we can't reject it, meaning it could be that's the actual real value. May not be, but it could be. We cannot reject that that's a possible value for the true mean. But we can't say it's definitely this because of the sample we got. You can't make that statement at all. So B is the correct answer. I don't know why this window is not bigger. Let's see, can I make that window bigger? There, okay. Move this out of the way. Check answer. Next question. Oh, we got an actual question, a new question, good. We're just on question 4 here. So what we might have to do is continue this tomorrow because I got some things I got to do here in a little bit. But we'll do a little bit more right now. We've been at this a while.
Yeah.
All right. So it says this accompanying data table shows reaction distances in centimeters for dominant hand of a random sample of 40 independently chosen students. So N equals 40. Okay.
Yeah.
Complete A through C. A says make a graph of the distribution. Okay, so now I got to do the share. We'll put this in StatCrunch. Okay, transfer that to StatCrunch. Open in StatCrunch. All right, and now what did it do? Stop share. Share screen. Okay. Let's see, is this the data? I think. What did it do there? Where did it put it? What is this? No, that's not right. Close that out. Close that out. Stop share. Share. That's what I want. Why doesn't that come up now? Why does it come up with this screen now? That's crazy. I did this correctly a bunch of times and now it's, what is this? No. Google Chrome, my StatLab data, right. There we are, it's selected. We say share. And I don't know where it went. Here, what is this? No. That's not it. That's very strange. What's this down here? It's in Chrome. Let's go to window maybe. Because it's not showing me other windows up here. Window. No, that's not it. I don't know why it's doing this now. It worked a bunch of times. Oh, you know what? Well, I'm wondering, because I show, let me do it that way. Wait a minute. Yeah, I'm doing the same thing I was doing earlier, and it's not transferring it. And I don't know why. Maybe, I'm wondering if the meeting itself, like, timed out or something. I mean, it's showing, we've still got this going here. Gallery view, what's gallery view? Let's try that, share screen. I don't know, Ruben. It's not coming up. I think maybe we'll have to call it here. So we'll do this again tomorrow. Is that good for you?
Yeah, what time?
How about I got a couple classes earlier. How about 3 o'clock again?
Yeah, 3 o'clock works for me.
And once again, I went through more explanation than I intended to, but it's going to help you if you understand where this comes from. But
Yeah.
I'm going to try to just get in and just click on the answers, okay, and get through this whole data set so people can see how to work these all the steps on these problems, okay? And we've covered a lot of the explanations, so I won't have to explain as much tomorrow. And we should be able to bust through chapter 7 problems, in an hour or less,
Right.
and
Yeah.
have all those done, and then you'll have this explanation also as a bonus, okay?
Yeah.
And I don't know why, it just changed. It won't pull that up now for some reason, but so we'll call it here. Thank you very much. I'll see you tomorrow, Ruben.
Thank you for the help.
You're welcome.